Okay, all right. Well, happy Friday. It's week 9 Friday. We got just one more week to go, and as far as this class goes, next week, I'll just kind of do bonus content. So I mean, maybe a little bit more PCA, which you will be tested on, and then we'll go from there. Okay. All right. So today, yeah, we'll introduce PCA. PCA stands for Principal Components Analysis. And I would say that your general idea here is you start off with a data set with a bunch of variables. And, there's a lot of times when you have a bunch of variables, those variables are often correlated. And what PCA does is it transforms them into uncorrelated variables. The goal is often to do dimension reduction. If we take advantage of the fact that kind of a lot of variables are correlated, can we reduce the number of variables and still manage to capture or convey the variation that exists in the data? When you have highly correlated variables, that comes with its own kind of set of problems. You got like VIF in that it becomes a little bit difficult to, well, not difficult, but just because of random noise in your data, your estimates for the slope on coefficient, your estimate for slope on variable x1 and variable x2, your coefficient estimates exhibit variation because of randomness. And if they are correlated, then now they're kind of a lot more sensitive in terms of just the random variation. Let's just take an example. So I don't know, like in 101A, did you ever look at like a housing data set? It seems to be like a very common kind of problem example type of data when you work with in like regression and stuff. And I don't know what housing data set you guys looked at. There's all kinds of housing data sets out there, and some of them are like problematic and things like that. But one of the, this is just some made-up variables or some fictional data set. But you might have something like livable square footage versus like total square footage, which might include a basement or something that technically doesn't fall under the livable square footage because there's, I don't know, rules about stuff. In California, we don't have basements really, but I don't know. Maybe somebody has a basement in California, but in general, not really. Okay, and then you got number of bedrooms, bathrooms, lot size. Is there a pool? What kind of roof you have? The quality of the kitchen. There's also like things related to the location or zip code and local school rating. Maybe the median price of the surrounding neighborhood, stuff like that, right? And you got, you might have like 40 variables or something. Can we reduce the number of variables? And I would say a lot of these variables can kind of just be grouped overall into one that's related to size. In general, as square footage goes up, then number of bedrooms, number of bathrooms will also go up together. And then you have maybe some kind of variable rating, just the overall like nice feel of the place. Like, does it feel new and clean, or does it feels like run down and needs to be fixed up? That kind of stuff, right? And then one is, I would say the last one would be kind of neighborhood desirability. How kind of nice is this neighborhood? Is it, and that might be reflected in things like the school ratings or crime rates or the local income level or things like that, median price of surrounding homes. And I would say, if you have those three things, that's going to capture a lot of what's offered in the housing housing data set. And can we go from a whole bunch of these things down to just maybe a few variables? Okay. Other examples of dimension reduction. Okay. And I don't know if this is so we got they're useful, but I think we are kind of familiar with some of these things. And we also realize, too much dimension reduction can also be a little bit harmful, right? So like GPA, that takes your entire academic kind of performance, and I don't know, you could, I guess, have a variable, like you could imagine, I don't know, some crazy data set where it's like each row is a student and you have a column for, I guess, every single class offered by the university. Okay, and most of these will be zeros, that like students just didn't take that class, right? And then you have column 1 for 102A, and then another column for 102B, and another column for 101, whatever, and and you have like a different thing, and then overall GPA basically just boils it all down, basically like an average, and reduces everything down to a single number, right? SAT or GRE scores or whatever takes this complicated idea of, quote, I don't know, intelligence probably isn't even the right word, but just like, some amorphous idea of performance, academic performance or something, and it boils it down to maybe 2 or 3 numbers, usually a verbal score, a math score, and a writing score or something. Credit score takes things like financial trustworthiness and reduces it to a single number. In sports, you have different kind of like numbers. You have passer rating for like NFL, but in like baseball, you have like wins above replacement, which is kind of this complicated measure. In basketball, you have like, I don't know, different kinds of things, right? Or, say at the Olympics, you have these track and field events like decathlon and pentathlon and heptathlon and all of these things. And basically the athletes are competing in, multiple events, but then you have to rank them at the very end in a one-dimensional way. You have to say this was the best and this is the worst, and this person gets gold, silver, bronze, right? But you have to take into account basically 10 different performances, right? So if this one athlete does well in like 8 of them but poorly on 2 of them, how do you figure this out? Okay, and so all of these systems are ways to reduce dimensions. Sometimes dramatic reduction, down to just one number. A lot of these things are just one number, and others, you say, okay, well, we'll keep 2 or 3 numbers or something like that, right? So these aren't necessarily principal components analysis, but this is the idea of dimension reduction. And by reducing the number of dimensions, it just makes it easier to make comparisons, right? When you only have one number to compare, you can easily kind of order them from greatest to least, right? But again, that simplicity is, also the flip side is that it's a little bit harmful, right? In that, when you think of like, if we use GPA, then you get like these little like wonky things that happen where it's like, okay, I want to take this class because it's interesting to me, but I'm afraid it's going to affect my GPA, so I'm not going to, right? Because we understand that like there's just not, when things get reduced to just one score, you lose a lot of nuance, right? And it would be nice if we could just be like, oh, okay, we're gonna just kind of study things we want to study, and then we, can we like uncheck the box there or something that says like shouldn't affect our GPA very much or whatever, right? And I don't know, maybe that's accounted for when you have like your regular GPA and then you have like your major specific GPA and things like that. And so that's like, but overall, things like, I don't know, like in high school, this was a thing when I went to high school, and I don't know if it's a thing today. So like your advanced and honors classes counted for like 5 points, and then your regular classes counted for 4 points. And you had like, at our school, you could take driver's ed as a course, and but if you took it through this, or you could also take it privately and get credit. And if you took it through the school, it would count, like even if you got an A, you'd get 4 points. But if you were like a 5.0 student, that would bring your GPA down, versus like if you took it privately, like it wouldn't get factored into your GPA or something. Does that sound like something that could have happened? That was the thing. And it was like, oh, okay, well, if you were concerned about your GPA, you would take it privately to avoid the 4.0 getting factored into your, 5.0 GPA type of thing. Okay. Well, anyway, here's another kind of idea of dimension reduction. Is so in real life we have dimension reduction, and we can see it visually, and it's the idea of casting a shadow. Okay, so you stand outside, your body casts a shadow. Basically, every object casts a shadow. I mean, every light source will cast a shadow, right? And if objects exist in 3 dimensions, and I don't know if I can show this here, okay? If I put my hand here, it casts a shadow, right? And if you see this, that's very clearly a hand, okay? And I would say this image, we're not losing a ton of information, right? You lose a little bit of like, I guess, like, I don't know what my hand looks like, right? Versus like if I hold my hand like this, you can probably still tell it's a hand, but you lose a lot of like the information, right? And if I hold my hand, I don't know, something like this or whatever, like there's certain orientations where you lose more information than others, okay? Versus, like with a pen, okay, if I hold it like this, right, and basically all we see is just this tiny little circle, it's hard to tell what exactly I'm holding, okay, if you only see this shadow here, okay? Versus if I hold it sideways, that's very clearly a pen with a little, I guess a little hook or something. Turn it this way and you lose lose sight of that hook. So certain orientations of these 3D objects have better looking shadows, right? And so, depending on how the object is held, the shadow that it casts, might resemble the object, it might not. And so, the idea here is we want to pick a lower dimensional projection of our high dimensional data that still kind of resembles the original data. That's the goal. So mathematically, the way we kind of define this notion of our data, our lower dimensional projection resembling the original data, is we say we want a projection that captures as much of the variance that exists in the original high dimensional data. So your original data has a certain amount of kind of variance, and when you reduce the number of dimensions, like if you reduce the number of variables, you're going to lose some of that variance, okay? Unless you have like 2 variables that are perfectly collinear, then anytime you cut down the number of variables, you're going to lose some of that variance, right? It's kind of like the idea that If you had linear regression, every time you add a variable, you can kind of bump up your r-squared value. And if you take away a variable, you're going to lose a little bit of r-squared value, right? So if you just say, all right, we want to kind of capture the total variance in our data, every time you remove a variable, you're going to lose a little bit of it. But can we, remove variables in such a way that we're still, with the remaining variables, we're still capturing a lot of the original variance, right? So it says if we reduce the dimensionality of the data, we can't capture all of the variance that exists in the original data, but we just want to find one that still has a high amount of variance. And so we are going to, what we're going to do is we're going to search for a lower dimensional projection that maximizes the variance in the resulting projected space. Okay, let me give you your first view quiz answer, which is the letter E. E as in elephant is our first answer for today, E. Okay, so what does it mean to kind of project our data, and what does this look like? So we're going to say our original data has m dimensions, some number m, okay? And so when you're looking at, say, the nth value, nth observation in the original data, it consists of m values, right? So that's what we have. So we have a vector of length m, and what we want to do is we want to take this m-dimensional data and project it down to only d dimensions, where d is a number less than m, okay? And so after we project y, which exists in m dimensions, down to d dimensions, we're going to say we have the kind of equivalent x value. The nth value in x is a vector of length d. Okay, so perhaps your original data exists in 3 dimensions, and you have, your original data is a coordinate in 3 dimensions, and we're going to transform it from y down to x. X exists only in 2 dimensions, okay? So what PCA will do is it's going to define d vectors, okay? One vector for each dimension in x, okay? And those vectors are each going to be m-dimensional. Each vector will have m values in it. And we define our projected values as basically the product between the d vectors, our weight vectors, multiplied by original data. Okay, and so what this means is that each of the values in x, okay, the elements in x sub nd in the projected data are just linear combinations of the values in y, okay, each of which is weighted by the values in w. So I don't know. So like a simple example is just adding your scores together, right? If you took the SAT, you get a math score and a verbal score, and there was a time where there was a writing score, but did they get rid of the writing when you, you have a math and a verbal, and so you can, when somebody say, how did you do on your SAT, you can say, oh, I got this on math and I got this on verbal, right? Or you can just say my total was whatever, right? So the total is basically a linear combination. So you're going from two values, a math and verbal, down to a single total score, and that total score is just the sum, okay, a linear combination of the 2 values, right? So that's an example of dimension reduction, where your W is just 1 and 1 because you're equally weighting your math and verbal, and then you multiply it by your original 2-dimensional data, and you get just a 1-dimensional output. Okay, and you can imagine some kind of wonky system where the school's like, okay, for us, verbal is more important than math, and so don't give me your SAT score, which is a total, but weight your verbal, by 2, and your math as 1, and you could do that, and now you have this new number. It's also 1-dimensional, but that one emphasizes the verbal score more, right? And you can kind of have this opposite thing. And so basically we could change the values in W, and we're going to get different linear combinations. So if we wanted to go, say, from 3 dimensions down to 2 dimensions, what we're going to have to do is we're going to have to define 2 of these weight vectors. Our first weight vector will tell us, how much, if our original data is y1, y2, y3, how much do we weight each of those things? y1, y2, y3 gets weighted this much, and they get combined to form W1. And then our second vector will also be, how do we combine y1, y2, y3, but we're going to give different weights, and we'll get a different number, okay? And so when we multiply our y observation, we get y times W1 will give us basically the first value in x, and then y times W2 will give us the second value in x, okay? And that's the idea here. So we're just doing linear combinations. So little recipes of, how do we combine each of these things so that we get some kind of value at the end. So what we want to do is we want to choose our weight vector so that the variance in the projected space is maximized, okay? And so the first vector, so our first weight vector, W1, will be the set of weights so that the variance in the projected values, that is kind of the first x component, is as high as possible. The second vector, W2, will also maximize the variance in our second x value, okay? But it has to be orthogonal to W1. That is, if we take the product between W1 and W2, their product is 0. And then, if you have a third weight vector, if you're projecting it down to 3 dimensions, then, we also want to maximize the variance in the projected space, but it has to be orthogonal to all of the previous things. And there's a typo here. So Wi times Wj is going to equal 0. So this should be a j here. Is going to be equal to 0 anytime you take the product between any of these weight vectors, okay? And then we'll kind of put a constraint that the length has to be 1 of each of these weight vectors. Okay. A lot of kind of just defining of stuff here. So we'll start by looking at our first weight vector, okay? And we're going to say, okay, we want to just, this is a problem where we say, okay, well, we want to maximize the variance. If we just project it all down to 1 dimension, how can we capture the most amount of variance here, okay? So to make our life easier, what we're going to do is we're going to center the original data, okay? So we're just going to take all of our y values, calculate the mean of y, subtract the mean off of y, and that will project it down. That will center our data so that the mean of y is equal to 0. Okay, so all we do is we just subtract off the mean, and that centers our data. Now the mean of y is equal to 0. Okay, and then the next thing we will do is we're going to look for a solution to maximize the variance here. Okay, so to keep it easier, we're just going to say, all right, we're going to just reduce it down to 1 dimension, and so we're going to say we're just going to look for this one vector w, okay? Our original data in y is of length m, and we're going to multiply it by w, which is also going to be of length m. And so we have, w transpose y, and this will give us a single scalar value when we do this, right? So we have m values, and we're just going to m values in y, and we're going to combine them in some kind of way so that we get one value out. And so we're just going to use the definition of the variance here. I know this one's divided by n rather than n minus 1, but I guess this would be our biased value of the variance if we treat this as the population or something. Okay, and so all we do is we just say, okay, we're going to just take each value in x, subtract off the mean, square it, add it up, divide by n, right? So this is going to be our variance. And what we want to do is we want to maximize this quantity. Okay, so if we have this, if we know that the mean of y is 0, then we can also say the mean of x is going to be 0, because x is just a linear combination of the values in y. So we have just w times y, and we know that the sum of all of our y's divided by n is going to be 0, okay, or really the sum of the y's is equal to 0. And so if we have w times whatever this is going to, the total, this is going to end up being 0, okay? So the mean of x is 0, okay? And that's why we want to center our data, because that's going to make our life easier. Okay, so if we look at what is our variance here, okay, we can say, all right, we have the sum of x minus x bar squared. Here, I'm going to just subtract, we know x bar is 0, okay, so this just becomes basically our xn. We can say our xn is w transpose y sub n, quantity squared, okay? And so, this is a single scalar value here, but we can expand out the terms, the vector terms, and this would expand out to be w transpose y sub n transpose w. Okay, and then we have this as a summation 1 over n here, and we say, okay, well, you know what? The w's are not affected by the subscript n, right? So the y values are different for each n observation, but the w's are the same for all of them, so we can pull those out of the summation. And so we're going to have w transpose times this whole thing, okay, which is a m by m matrix, times w, right? So this is, the end result here is still just a single scalar value, but we've turned it into a 1 by m times an m by m times an m by 1. So this is a way for us to kind of express our variance here. I said our variance expression can be simplified. I don't know if this is arguable, right? Debatable. Okay. So, well, one thing is, okay, what is this? This, if we know the mean of y is 0, okay, this quantity right here can be said, okay, well, this is just the variance or the covariance matrix of y, right? Because if we say, okay, well, what is your variance or covariance matrix y? You have, basically y minus y bar, yn minus y bar transpose. This would be your variance covariance matrix. And here we know that y bar is equal to 0, so this quantity right here is equivalent to our covariance matrix here. Okay, so our variance here is now w transpose times basically your covariance matrix of your of y after y has been centered times w. Okay, so what we want to do now is we want to maximize this. We want to maximize this quantity, the variance, right? And we have one constraint, and that is that w has a length of 1. Okay, so how do you maximize something subject to a constraint? Lagrange multipliers, right? That's how we do things, right? This is how we maximize stuff subject to a constraint, right? So we have this constraint, w transpose w is equal to 1. That's the kind of to limit our the length to be 1. Okay, so we're going to say, okay, let's maximize this, with the Lagrange multiplier So we're trying to maximize this thing, W transpose CW minus, when do you guys cover Lagrange stuff? Is that 30?
Last chapter, 32A.
32A. Okay. All right. Good times, right? Okay. It's like, when are we going to use this? You actually use it. Okay, so here we have this, right? And then here's our Lagrange multiplier, lambda W transpose W minus 1. Okay. And so just what we're going to do here, we'll take the derivative. We'll set it equal to 0. Okay, and so what do we get? We get 2CW minus 2 lambda W. Set that equal to 0, and now we need to solve for W. All right, so now I get CW is equal to lambda W. Does this look familiar?
Oh my God, it's an eigenvalue.
Right? Yeah, it is. It is, right? So C is a matrix. We have a matrix times a vector. Matrix C times vector W is equal to a scalar times a vector. All right. So that's an eigenvalue eigenvector thing. Okay. So W. So we want to solve, right? Find a solution W that fits this equation where C is kind of our covariance matrix, lambda is a scalar, so we have matrix times vector is scalar times vector, and so the solution is that W is the eigenvector of C, and lambda is the eigenvalue. Okay, and it turns that the eigenvalue eigenvector pair with the highest eigenvalue will be the projection with the highest variance, and then kind of your next highest eigenvalue will correspond to W2 and so on. So this is the joys of eigenvectors and eigenvalues. And so if you recall eigenvectors, eigenvalues, and how they are, that's great. I always love watching the 3 blue, 1 brown video on eigenvalues. Okay, so okay, how do we just go there? Okay, so I don't want to play this here. Oh, we got a commercial here. Okay, but look this up. 3 blue, 1 brown, eigenvectors and eigenvalues. Oh, it's already 6 years old, this video. Okay, well it's really great. Okay, I've already given it a thumbs up. I can't like it again. But yes, watch this. Actually, the entire series from 3 blue, 1 brown on linear algebra is really great. Okay. Essence of linear algebra. This whole, oh, look at, there's nice little music too. 16 little videos, but watch them all. But especially the one on eigenvalues and eigenvectors, because if you think of matrices as a way of kind of transforming your coordinate plane, then what is an eigenvector and things like that is pretty good. Okay, so anyway, that's the solution. And so the summary for kind of finding our principal components analysis to say go from M dimensions down to D dimensions is first we're going to center our data so that the column means are all 0. We're going to compute the covariance matrix C, and then you find the eigenvector, eigenvalue pairs, and you'll do that. So I didn't put in slides for like how to do eigenvectors and eigenvalues. But I'll say you should know or review how to do this. Okay, so you have some homework where you kind of do this stuff, and then like on the final exam, and I'll talk about what kind of stuff we'll put on the final exam next week. But on the final exam, I think it is reasonable to give you a 2x2 matrix and say find the eigenvalues or eigenvectors of a 2x2 matrix. Okay, more than 2x2, and then it's like, oh my gosh, this is it's a pain. It's a pain to do that, right? But finding the eigenvectors and eigenvalues of a 2x2 matrix, I think, is reasonable. Okay, and actually, maybe I won't even give you like, if I give you, say, four or five values in 2 dimensions, can you find the covariance matrix yourself by doing basically this operation? Okay, and so if I give you like 5 values in 2 dimensions, I'll talk about this next week. Okay, but 5 values in 2 dimensions. Can you get your 2 by 2 covariance matrix? Can you figure out your eigenvalues, eigenvectors? And so you kind of do a little bit of this in your homework. Let me see. Do I have? Where did my PCA example go? Okay, well, I don't know. So this was your homework. Oh, okay. So your homework, basically, I walk you through this process. But we'll take a quick look at doing principal components analysis. So there's a PR comp, which will do kind of principal components analysis. Oh, this is a Python script. So I don't know, let's say x is the values 1 through 10, and y will be x plus r norm 10 with st equal to 3. Okay. And let's round this to okay, so if I do plot x and y, so here are my values here, okay, 0 through 10. So x is 1 through 10, and y is, we got some noise here, okay. What's the correlation between x and y? We have that, and then so I'll make my y matrix by C binding x and y. Okay, so here is my matrix y, and what we'll do is we'll do column means of y. Okay, so our centered y is going to be transpose of y minus column means of y, and then you need to transpose that back. So I think this will do it. So if I do column means my centered matrix, I have 0. Okay. All right. And then, okay, so we'll take the variance of our centered matrix, and then I can do eigen on variance of this. So these are my eigenvectors here. I'll take the first column. Helps if I spell it correctly here. So this will be kind of my first principal component. Okay, so I can take, so here's my data here. Whoops, my centered data. So if I plot, let me just do aspect ratio 1. Okay, so this is still my data, and what we're going to do is I'm going to project this down to one dimension. And the idea here is it's kind of like I'm going to just draw a line, okay? And it's not the regression line, but it's kind of what line is it? We're going to draw kind of this line here, and then we're going to basically cast a shadow. So where's my stick? Okay, so basically you can imagine this a line here, and then shining. Basically, I'm going to have like a light source over here, and then all of these dots are going to get cast down. I guess this one would get cast this way, but onto points here, and we're going to have kind of like an ordering from least to greatest. Versus like the bad projection would be if I put kind of the ground over here, and I put the light source up in the top right corner, and if I cast the shadow here, then the resulting variance of our data is going to be the last one, right? So right now we have variable basically x1 or x, and this is, if we look at the variance in x1, this is basically just dropping everything down to the floor here, and we capture the variance in this direction. We could do it this way, and everything kind of gets pulled this way, and we would capture the variance here. The one that's going to maximize the variance is going to be the one that kind of does something like this, okay? And so, I would take my PC1 and multiply by y. This is our favorite thing. Oh gosh. Am I doing this wrong? X is W transpose Y. Do I need to do Y times W? Oh yeah. X is YW. Sorry. Okay, so PC1. This is going to kind of project my data down into one direction. If I do the same thing with the second, okay, this is going to be the projection here. So I guess how do I do this? Okay, so I can plot. So here's what happens if you just project it down to, oh my goodness, what did I do?
C is capitalized.
No, thank you. Okay, so this is like if you just project it down to one dimension. Okay, this is the result. If you keep both principal components, then you're going to retain the two-dimensional structure, and this is just a let me delete this one. This is a rotation. I don't know if you can see it. Okay, so you can kind of see like there's this little thing here, and we're just taking this and we're like rotating it. Okay, so the resulting plot over here is a rotation of it. Okay, and so this is the kind of direction that maximizes the variation, and then the second thing just captures the leftover variation. And because the original data only had 2 dimensions, when we rotate it here, this will capture 100% of the variation. But if we take these things and I just reduce it down to 0, okay, so just imagine a horizontal line, and all of these things just kind of dropping straight to the horizontal line, then you get this, right? So this is, so just imagine a horizontal line, and so these two things are very similar to each other, okay, as far as the x1 direction goes. And this is just it's just, I don't know, can you kind of see what's happening there, right? We're just dropping the second dimension, okay? And so when you reduce it down to one dimension, basically everything just becomes just a simple ordering, and you lose any of the variation here. So we're starting off with data that look like this. We basically rotate it, and then now that we've rotated it, that maximizes the variation, we can kind of just drop the second dimension, and there's kind of like, how much information are we losing when we reduce it down to one dimension, okay? Yes, you do, again, dimension reduction to some degree is harmful in that you lose nuance and detail, but it's also, it simplifies a lot of kind of matters by, you only have one thing to think about rather than two things, right? And basically the fewer variables that you have to kind of keep track in your head, your decisions are easier, okay? But again, at what cost? Okay, that's that. Oh, how many? I forgot to give you view quiz answers. I have to give you two more? Or, yeah, okay. So the last one are C and B. So second answer is C, C as in cat. Third answer today is B, B as in bear. Okay, that's it. I've got a little bit more PCA stuff on Monday, and then but yeah, we'll take a look at that, and then I guess bonus lectures week 10. All right, thanks for coming, guys. I appreciate you guys. All right, have a great weekend, and we'll see you next week. Yeah.